Thank you for the introduction. So today we'll finally arrive at the last part of the title of the series of lecture. We'll finally say something related to log Gromov Witten invariants. So last time we discussed the way to organize the wall-crossing behavior of quiver Donaldson-Thomas invariants. And while doing that, the output were some pictures involving trees and trees embedded in vector spaces. So things looking like tropical curves. And so it's natural to ask if these tropical curves are actually the shadow of some honest, complex algebraic curve somewhere. And so doing that would be the main story today. I will explain the correspondence between quiver Donaldson-Thomas invariants on the one hand, and on the other hand, some complex algebraic curve, which will actually be log curves, as in Bernd's lectures. And there will be actually two stories, one story involving log curves in toric varieties, and a second story involving log curves in cluster varieties. And so this main correspondence will involve quiver DT invariants, but if I have time at the end, using the fact that sometimes quiver DT invariants can be related to geometric DT invariants, we might say something interesting involving geometric DT invariants counting current sheaves on Calabi-Yau threefold. And the early version of the story I will be talking about is due to Gross, Ponai-Zibert around 2009. We describe essentially log curves in two-dimensional toric varieties and cluster varieties, and deduce from that a correspondence with DT invariants of the Kronecker quiver, which is a quiver consisting of two vertices connected by a bunch of arrows. And around this time, this correspondence was sometimes called the Kronecker quiver correspondence. And so one of the points of this lecture is that it's actually not really special to the Kronecker quiver, but it's actually valid to a much broader class of quiver. So let me recall some annotations we introduced last time while talking about Donaldson-Thomas theory of quivers. So I denote by Q a quiver and W a potential for Q. And so in this lecture, I will always denote by D the number of vertices of the quiver. And I was denoting by n what was before denoted by gamma, which is the lattice of dimension vectors. So it's just z to the d with a natural basis indexed by the vertices of the quiver. And we introduce this dual lattice M and the corresponding real vector space MR. So it's just a real vector space of dimension d. And then for every dimension vector gamma in the lattice n, we explained that we could think of a point theta inside the hyperplane gamma perp inside this vector space MR as defining a stability parameter for quiver representations of a dimension gamma. And so for every choice of such gamma and theta, we add some integer omega gamma theta, which is a DT invariance, Donaldson-Thomas invariance of the quiver with potential, counting theta stable representations of dimension gamma. And key fact of last time lecture was the fact that inside this upper plane gamma perp of possible choices of stability parameters, there is a very particular point, the attractor point, that I denote here by theta gamma, which is obtained by contracting with gamma the skew symmetric from omega, which naturally encodes the combinatorics of the quiver. So last time, while describing the wall-crossing formula, the algebraic structure was controlled by this skew symmetric from omega on the lattice n, which is defined by the fact that omega of the basis vectors EIJ is Aij minus AGI, where Aij is the number of arrows from I to j. So just the adjacency matrix of the quiver skew symmetrized. So we have this special point, and then we define the attractor DT invariance as being the DT invariance at this particular point. So I was denoting by omega gamma star the attractor DT invariance. And one reason to care about this attractor DT invariance, so last time we mentioned that in many cases they are extremely simple, where this notion of trivial attractor DT invariance. In many cases, these numbers are just 0 or 1. So sometimes they are very simple, and they can be used to reconstruct the general DT invariance. And last time we mentioned essentially two statements. One, which is just some iterated application of the wall-crossing formula, which leads to an expression of the DT invariance omega gamma theta, or rather the rational version that I denote by omega bar, as a sum of all possible decomposition gamma into sum of vectors gamma 1 to gamma r, some easy combinatorial factor and a less easy combinatorial factor f r theta of gamma 1 gamma r, and then the product of the rational attractor dt invariance for the vector gamma 1 gamma r. And these not so easy combinatorial coefficients f r theta could be naturally expressed into a sum of trees that I will refer to as attractor trees, which live in the vector space MR. So here on the picture, it is a tree which is represented in red. It's a rooted tree starting as upon theta. And then we describe this move of going in a straight direction, in the direction of the attractor point for gamma. And then sometime you hit a wall for the dt invariance. And at this place, gamma, and this wall corresponds to a splitting of gamma into some gamma I. And then you branch your tree, and you continue into the upper plane gamma I perp, and then you move towards the attractor points for the gamma I, and then you iterate and you sum over all the possibilities. And each of these trees itself contribute a non-trivial contribution FRT theta, which in principle can be determined simply from the wall crossing formula of the universal Joyson conservative sum of wall crossing formula, but because this formula is kind of complicated, these coefficients themselves are not so easy in some way. And so what we explained last time is that there is an alternative representation of these coefficients given by this flow tree formula, which is an alternative actually explicit combinatorial description of this coefficient f r theta, where instead of summing over these attractor trees embedded in MR, we could be tree of any valences. Here in this flow tree formula written in blue, you sum over binary trees, and they are like combinatorial trees. They are not embedded into a vector space in the way I phrased the formula. They're just a sum of a combinatorial type of binary trees. And each binary tree has a very simple contribution. You take the product of the vertices of this binary tree, and there is a very simple contribution determined by the skew symmetric form omega. And there is a slightly more tricky coefficient epsilon, which is either 0, 1, or -1, which we can be recursively calculated by following a flow on this binary tree. So there is essentially these two stories, the one involving these attractor trees in MR, and the one involving this binary tree. And I will take as starting point the story involving attractor trees because it's the one which is closer to tropical geometry. Here we really have embedded trees inside MR. So they look like tropical curves. They look like genus 0 tropical curves because they are really trees. They are graphs of genus 0. And so this suggests that this contribution indexed by these attractor trees, or the full sum over these attractor trees, might be related to some honest count of rational complex algebraic curves. And the first main statement I want to discuss today is a theorem of this type, saying that this coefficient f r theta gamma 1 to gamma r, which are these kind of universal coefficients reconstructing general dt invariance from attractor dt invariance. They have some geometric interpretation as some appropriate counts of rational log curves in a toric variety. So to explain this statement, I need to explain which toric variety we are talking about. So our attractor trees are trees living in the real vector space MR. And in general, as we learned from Bern's lectures, the tropicalization or tropical curve live in the tropicalization of log varieties. And for the case of toric varieties, this tropicalization is essentially the fan of the toric variety. So we like to consider a toric variety whose fan live in this real vector space MR. And here there is maybe some unfortunate notation. So in toric geometry, there is standard choice of what is n and what is m. And here the convention is reversed. And one of the explanations of this story is useful in the context of mirror symmetry where the role of n and m are swapped. So in this lecture, MR is where the fan of our toric variety will live. And so we want to describe this coefficient FR theta gamma 1 to gamma r. So in this story, I will fix once and for all this gamma 1 to gamma r, which sum to this vector gamma. And then if you remember what our tree looks like, our tree looks like that. And if you look at the various directions of the edges of the tree, you will see that, so first of all, there is a root, which is here at the point theta. And the edge ending at the root is in the direction minus this contraction of omega with gamma. And on the other end, we have the leg. We have some legs going to infinity. And this leg going to infinity go into the direction contraction of omega with gamma j. So we have these particular directions in our vector spaces which prescribe the asymptotic of your tree. And so it's natural to consider sigma a fan in the real vector space which at least contains these rays. So I will consider a fan sigma containing these rays spanned by this omega contracted with gamma j. And I will pick, for convenience, a fan which is a fan of a smooth projective toric variety. So you just look at this collection of rays, and you just take any smooth complete fan containing this collection of rays. And there will be a corresponding x sigma, some smooth projective toric variety of dimension d. So here there is some choices involved by picking this fan. So the numbers we will be discussing, this count of log curves, will be actually independent of these choices. So we get a toric variety, and by construction, because these rays spanned by this contraction of omega with gamma j are part of the fan, these rays correspond to some toric divisors of the toric variety. So I have particular toric divisor dj for every j from 1 to r. And then to set up our accounting problem, we will make some additional choices. For every j, we'll consider some hj inside dj. So hj will be some hypersurface inside the divisor dj. So it's a codimension 1 inside some component of the boundary. So it's codimension 2 in the total space. So here I draw a picture. This three-dimensional thing is supposed to be a picture of our toric variety. The kind of quadrilateral faces are the toric divisors. And in green, I've represented these hj. And these hj, what they are concretely, they are just defined by some very simple equations. They are defined by the equation z to the gamma j prim, a primitive vector in the direction of gamma j, equal to a constant, where you view that as an equation on dj. So essentially, you use the information about gamma j to write down these locus. And it's an exercise in toric geometry that actually this definition makes sense, that this monomial z to the gamma j prime, a priori it's a function on the big torus, it starts with d, but you can check that this function is actually a regular function along the generic part of dj, and so you can use this regular function to define some hypersurface in dj. And so this hypersurface has a concrete equation of the form monomial equal to a constant. I denote by cj this constant, and this constant lives in c star. And we pick any constants we like, and later we will argue that things are nice if these constants are in general position. And now the kind of curves we want to consider. So we fix this toric variety, and we fix this hj, which depend on this parameter cj. Then once these choices are made, you can look at a moduli space of curves. And you just look at curves which look like the tropical picture. So you look at general zero stable maps to your toric variety, C with some number of mark points. So there'll be P1 to PR, some mark point, which will correspond to the leg of our tropical tree. And an extra mark point, P infinity, which will correspond to the root of the tree. And then we impose a condition that is mark points P1 to PR. They go to these loci H1 to HR. So the position of this mark point is constraints inside the divisor D1 to DR. And in addition, you impose the fact that this curve intersects the toric boundary only at the images of the mark points P1 to PR and P infinity. And in addition, you impose contact order with the boundary determined by these directions of the legs and edges in the tropical curve. So this contraction of omega with gamma 1, gamma r, and with minus gamma. Okay, so this curve looks like this red curve on this picture. There is this P1 PR, which goes to this green locus in the boundary. And then the curve is hitting the boundary in only an extra point, which is P infinity. And to define this moduli space here, I just use ordinary theory of stable maps. I just look at these stable maps, which has this nice intersection pattern with the boundary. They intersect the boundary only in these R+1 points. But of course, the issue is that this type of moduli space is non-compact in general. Yes?
Well, does it give this contact order? Because those things are interspective.
Yeah, so there is two answers. So one question is, I refer to Prin's lecture, which explains in general how to think of points in tropicalization at contact order. But here, actually, I made some nice choices. So for example, the ray, iota gamma j, is part of the fan. So this vector here, I can write it as a multiple of a primitive vector. And then it just means, so my curve here will, so f of P1 is in D1. So I want the contact order of my curve with this divisor to be this multiple of a primitive vector, the divisibility of this vector. So from the divisibility of these vectors, you get a kind of naive geometric contact order with the divisor D1, D2, DR. Sorry?
Why do you demand that f of pi and hi rather than just f of pi and di?
Yeah, so, okay, so probably the true answer is this thing will give the right correspondence. And actually, it's related to the fact, okay, maybe there is a better explanation, which is that these trees have these legs living in this upper plane. Okay, where it here, for example, in this picture, the legs going to infinity always live in this upper plane gamma I perp. And this upper plane gamma I perp, there are some kind of tropical version of this loci hi, roughly. But yeah, at this point, I've not really fully motivated this definition. Just say we look at this space of curves. And in general, each time you look at this kind of problem, like some curve with some prescribed intersection pattern with a divisor, there is no reason for this moduli space to be compact, because the curve is a moduli space of stable map. The curve, for example, could have a component falling entirely into the boundary in some limit of curve of this type. Maybe in the limit, these conditions at the intersection point with the boundary consists of finitely many points can fail in the limit of a family. And so we learned from Prin's lectures that there is a nice way to address this non-compactness issue. So log geometry provides a natural, nice compactification of such a moduli space. So I will denote by m bar the same moduli space, but in addition, I put log in my definition. So instead of stable map, I look at stable log maps. And of course, it is a kind of moduli spaces that Bern introduced. So maybe if I need to be fully precise, they're really like basic stable log maps, the one forming nice moduli spaces. And by the general series that Bernd describes, this space is as nice as usual moduli space of stable maps. They are proper delineant for stack. So what is important is that in this moduli space, the curves do not look all like that. But in the boundary, the curve can have components which are contained into the boundary of the toric variety. So actually, in this particular toric genus 0 situation, this moduli space is even nicer than usual. You don't need virtual techniques. You can argue that if you choose this constant Cj's, defining your Hj in a kind of general way, so if you pick this constraint Hj in a kind of general enough position, then this moduli space is of the expected dimension. And you can check that the expected dimension of this moduli space is d minus 2. So remember that d was the number of vertices in the quiver. It's also the dimension of the real vector space where the tropical pictures are living. And it's also the dimension of the toric variety. And actually, this moduli space not only is of the expected dimension, but it is log smooth over the trivial log point. So as Bernd explains, this moduli space is as himself a log structure. And so you can think about them in a concrete way as defining, as in particular, inducing a stratification of your moduli space by tropical types. So here is a kind of rough picture now of the moduli space itself. And for each of these strata of the moduli space, there will be a corresponding tropical type. So if I take a curve in the interior of this moduli space, if you look at such log curve, then its tropicalization will be a single tropical curve. So this log curve will be like a smooth curve over the point with trivial log structure. But if you go to some kind of codimension 1 boundary, then your log curve will live over a log point with, for example, a monoid like n. And the tropicalization will be a one-dimensional family of tropical curves. And if you go to deeper strata, you get higher dimensional families of tropical curves. Here's a kind of a typical example to have in mind. If my toric variety, let's say, is P1 times P1 times P1, and if H1 here represented in blue, it is a vertical P1 in one of the P1 times P1 boundary. And if I look at curve like the red curve, so they just intersect H1, like D1 with contact order 1, and the opposite phase also with contact order 1. So this red curve in the middle of the cube is one of the curves in our starting moduli space defined here. So they just intersect the boundary in exactly 2 points. And the corresponding tropicalization of this curve viewed in the tropicalization of P1 times P1 times P1, which is R3, it just is a red line here. So I have one vertex, red vertex as the origin corresponding to the irreducible component of the curve. And there is a 2 rays going to the left and to the right corresponding to the 2 contact points with the toric boundary. The thing is like my generic curves in the moduli space whose tropicalizations are just a rigid curve. But so here you see in this example that indeed such a curve moves in a one-dimensional family. So d equals 3, d minus 2 is 1. I can just move this red curve up and down. And if I move up, for example, at some point I will hit the top part of the boundary and I will get this green curve. So this green curve is in the boundary of the moduli space. And its tropicalization is obtained is a one-parameter family of tropical curve looking like that and moving up and down inside this upper part. And similarly, if the curve is going down, at some point it will hit the boundary into this orange part. And the tropicalization will be this one-parameter family of curve here moving up and down. So it's always confusing. This tropicalization operation is really some dual intersection picture. So the things which are like generic from a geometric point of view are non-generic from the tropical point of view and vice versa. And in this example, if you really think to the moduli space is just a P1, like just a P1 parameterizing this curve moving up and down. And there is these two special points, this green point and orange point, where geometrically the curve is falling in the top part of the boundary or in the lower part of the boundary. So this discussion of this, yeah.
Would you say how this modular space depends on CG?
Yeah, that's also. That's how, like, so the Cj is like the position of the Hj, and so the claim is that as long as the Cj are in a general position, this moduli space, for example, at least its dimensions stay the same. So there should be like bad non-generic configuration where this moduli space becomes worse than expected. Maybe it becomes of higher dimension, or it becomes more singular. But at least if the Cj are like inside some Zariski open set, inside some C star to the arch set of choices, then the way it looks like will essentially stay the same. At least this tropical type picture will stay the same.
But I mean, the definition of this modular space?
Yes.
Like in the slide before.
Yes. Yeah, so the Cj that determines these upper surfaces Hj. So they kind of define where the points are going. Yeah, so they are maybe like not the kind of most honest moduli space of stable log maps. They are like moduli space of stable log maps with some kind of constraint imposed to some mark points. The mark points are restricted to live in some part of the divisor. Oh yeah, and here it's a genus 0 story. And because these trees are like do not have genus, and so we look at genus 0 curves. And this genus 0 condition is important to us, this niceness of the moduli space. So why is this discussion of strata of the moduli space important? Is because we want to get some numbers. But this moduli space I've described, this seems to be, they are of dimension d minus 2. So if d is strictly bigger than 2, you get some moduli spaces of positive dimension. And so you do not obviously get some numbers. And so the idea is that we'll get some numbers if you restrict to the 0-dimensional strata of these moduli spaces, which geometrically means consider the most degenerate curves in this moduli space. And by these discussions, these 0-dimensional strata are have combinatorial types, which correspond to maximal dimensional families of tropical curves, so d minus 2-dimensional families of tropical curves. So for example, in this picture, what we'll do, we have this one parameter of curves. We don't know how to extract a number out of it. But essentially, we get a number from looking at the green point and a number from looking at the orange point, which are like 0-dimensional loci. So in practice, what we'll do, we'll fix some rho, which is some d minus 2-dimensional type of tropical curves. So such, for example, in this example where d equals 3, either the green part of the picture or the orange part of the picture. And then you can look at all the 0-dimensional strata in your moduli space of this given type, and then roughly you count the 0-dimensional strata. And you get a number identified by GW rho x sigma. So I think Bernd, if not in the last lecture, in the next lecture, we'll discuss more systematically the fact that you can assign Gromov Witten invariants to stable log maps of a given type, tropical type. And so this thing is an example of this general thing you can do. So we get these numbers, these log Gromov Witten type invariants. And the important point is that they are indexed by this kind of tropical data, these d minus 2-dimensional families of tropical curves. And so now if I want to get a correspondence with the previous story, which was involving these attractor trees, I need to explain how to naturally get these d minus 2-dimensional families of tropical curves. Previously, I just have some fixed tree starting as theta and then moving in some fixed direction. But the claim is that each of these trees can naturally be first of all extended and then deformed into families of the type we want. So first of all, in this picture, these trees have some roots at the point theta. And if I don't like these roots, if I really want to have honest tropical curves, so in the description of tropical curves of log curves, you don't have things like roots, you have things going to infinity, legs going to infinity. And this toric situation, I can just extend this edge in a straight way going to infinity. So it's the first operation. I add this blue thing, just extend straight to infinity. And now the second thing I can do is I can look at essentially the chamber inside gamma perp. So remember there's this wall and chamber structure coming by the walls intersecting gamma perp, and I also have the fan decomposition of this space. If I consider all this decomposition together, I can look to the smallest chamber of this decomposition containing theta inside gamma perp, which is this green cone I've drawn here. And then once you have this green cone, you can move your point theta, the root of the tree, you can move it anywhere you want inside this green cone. And so this cone is of dimension d minus 1. But of course, if you move the point in the direction of the edge, you still get the same total tropical curve. So if you do that at the end of the day, you get a d minus 2 dimensional family of tropical curves. So here what I've described is starting from one of these attractor tree. Essentially, if you first extend and then move them in a kind of most naive possible way, you get the corresponding rho t, a d minus 2 dimensional family of tropical curve for which we can attach a log count. Yes?
What I don't understand is it looks rigid in these tropicals. You start from the tractor point in a specific direction and then you kind of graph it. It all is very rigid.
So the starting point is not an attractor point. The starting point theta is a point you care about. It's a starting point. And the claim will be the kind of thing we care about is determinants actually will not change if we stay inside this green chamber. So they end into legs which are in directions like essentially like parallel to the direction of the attractor points. So they do not go to the attractor points, but they go to infinity in some direction which is like parallel to the attractor point. And this thing can move, and this thing will move correctly. Yeah. Yeah, someone was pointing out correctly in one of my pictures of previous lecture, there was a wrong picture where the thing was going to the attractor point. And so this thing was a wrong picture. The correct picture is that it goes in the direction defined by the attractor point. And then you can see that this thing indeed will move. Yeah. Yeah, so this attractor condition is really the direction of this leg, but not a particular point that this leg should go through. And so the first main statement for today is this theorem telling you that this coefficient fr theta gamma 1 gamma r, which has this universal coefficient coming from the wall crossing formula, which reconstruct general dt from attractor dt invariance. They have this geometric description as a sum over these attractor trees of these log Gromov Witten counts of these zero log curve with tropicalization given by these families of tropical curves.
And d is equal to r, or d minus 2 is equal to r, or what is the relation between r and
yeah, so d was the number of vertices in the quiver, which is the dimension of the toric variety. And here r is not related to d. So in this universal formula, you look at ways to decompose gamma 1 into any sums of gamma 1 plus gamma r vectors. So r can be arbitrary. So here the r is related to the number of legs of the tropical curves, or equivalently to the number of these upper surfaces hi are fixed at infinity. Yes?
Could you comment how you define the Gromov invariant as a degree of the cycle? Is it
Yeah, that's right. So here it's because I claim it's there is some honest like stack of the expected dimension, and it's zero-dimensional strata. You just live in degree 0 homology, and I just take the degree of that over this proper moduli space.
So they live in the cycle system 0 to 1.
Yeah, that's right. Exactly. Yeah.
And is it virtual cycle?
Yeah. So here in this toric situation, because of this statement, the moduli space is like log smooth of the expected dimension. You can work with like an honest ordinary cycle, no virtual. But in 1 minute, we'll go to the cluster story, and then it will need virtual. So if you want this part of the statement, if you want, you could put virtual, and you will get the same answer. It just you don't have to put virtual in this particular situation. And just one line about the proof. So actually, the proof of this result matches two stories. So first of all, the story I described last time, which was simplifying or giving a more explicit description of this FR theta coefficient in terms of this flow tree formula involving these binary trees. And the claim is that this formula can be matched to a degeneration calculation of these log Gromov Witten invariants. So if you do if you break your toric variety in small pieces appropriately, and if you run some degeneration gluing technology in log Gromov Witten theory, developed by Gross-Zibert, Abramovich, Chen, then you can express your counts in terms of like more complicated log curve in a more complicated broken toric variety, whose tropicization will be made of these trivalent type of trees.
May I ask a question?
Yes.
So on the left-hand side depends on the quiver, no? You have a quiver, and then you define this F, this R.
Yeah, that's right.
So on the right-hand side, the X sigma is determined uniquely from the quiver, or?
Yeah, that's right. So the X sigma is really cooked up from this form omega, which is essentially determined by the which is determined by the quiver. And so what matters is what are these divisor di, in which we consider this hypersurface hi. These things are defined by this vector, which has this contraction of omega with a vector gamma I. And so this thing depends on the quiver. You should, in first approximation, omega is the data of the quiver. So maybe omega does not see loops, but yeah, the information is in omega. Like it is in the direction of these particular rays inside the fan, and how do they sit relatively to each other. So in the simplest case, like of you take a quiver with two vertices, and if gamma 1 is just 1, 0, and the other is 0, 1, then you will consider a toric variety which has at least two rays in this squared. And you can check that the determinant between these two integral rays will be related to the number of arrows between the two vertices if you go through the correspondence. So, yeah, so really this counting problem on the right-hand side is determined by the quiver too. Yeah. Yes?
How is it related to the separation structure constants for the databases?
So I'll make a comment for that maybe in like 10 minutes. And actually, I will not say much, but maybe in 10 minutes I will say something. Because now we'll say something about cluster varieties, and then it will be more naturally related to your question. So the main result of this first part was that in this universal formula, if you just look at these coefficients have some interpretation as counting log curves in some toric varieties. But you might ask, okay, what about the full DT invariant? Maybe can you give a log curve interpretation of that? And in general, you do not expect such a thing because you have these non-trivial attractor DT invariants, which in complete generality are not expected to have some description in terms of log curves. For example, they grow too fast, I would claim. But if you make the assumption that we argued last time happens in many situations, that these trivial attractor DT invariants are trivial, so it shows essentially that these numbers omega are 0 or 1, and they are 0 unless you have a basis vector or you're in the kernel of this form, then in this case, essentially this part simplifies very much. And so you might hope that this full formula, this full expression, has a log Gromov Witten interpretation, that the DT invariant itself has a log Gromov Witten invariance. And now we'll explain that indeed this log Gromov Witten invariant as an interpretation, sorry, this DT invariant as an interpretation as a log Gromov Witten invariant of a cluster variety. And so here, the first remark is that because of this assumption on the fact that trivial attractor DT invariants, then the gamma I vectors we consider in the decomposition, they are always, so gamma I now will always be proportional to one of the basis vector Ek. So now if you run the previous story in this particular situation, the rays in the fan of our toric variety will be of this form contraction of omega with now the basis vector Ei. And the hypersurfaces Hi also only depends on the basis vector Ei. So in particular here, the story only depends on the quiver, is no longer depend on a specific decomposition of gamma into gamma 1 plus gamma R. Yes?
So is that contraction now just the sum over the neighbors of the vertex? Ej of the neighbors of the
This thing? Oh, yeah, that's right. So if you think what it is, yes, it's contraction of omega with Ei, so indeed it will be determined by what is the number of arrows with neighboring vertex, that's right, yeah. So in the previous story, we had this toric variety and this Hi, which are like codimension 1 inside the boundary, so codimension 2 in the total space. And now we do something else. We can blow up this Hi. So this codimension 2 loci in the total space, you can blow them up. It's a non-toric blob because it's Hi are not toric strata. And so what you get as a result are denoted by X. It's a blob of our toric variety X sigma. And I denote by partial X the strict transform of the toric boundary. So you get a new pair X with this boundary of X. And it's a fact due to Gromov-Witten that if you look at the complement of partial X inside X that I denote by U, maybe up to possibly codimension 2 loci, this U coincides with the so-called X cluster variety or Poisson cluster variety attached to the quiver Q, which is something that maybe some algebraic or representation theory might care about. And so the traditional description of this cluster variety is by gluing some copies of C star to the D, which are indexed by some mutations of the quiver Q. And it's a result of Gromov-Witten that really the same geometry can be described in this kind of, in this language of non-toric blob of toric varieties. So here is clear, for example, by construction, there's obviously one C star to the D, which is the one coming from the toric variety. And here you don't see the others in an obvious way from this description. But the point is that this X actually can be realized as a blob of a toric variety in many different ways. And all these ways produce the various cluster charts on your on your cluster variety. And now instead of doing the count inside the toric variety, you might make a count inside this cluster variety. And so before we were counting curve with like R plus 1 mark points. And there was R mark points going to the Hi and one extra mark points going to the boundary. But now that we've blown up the Hi, we will forget the first R mark point. So we'll consider a curve with a unique mark point going to infinity here. And essentially, we replace the previous condition of intersecting the Hi by the condition that this curve lives in some homology class, which has some prescribed intersection number with the exceptional divisors created by this blob. Okay, so I will not go into the details, but roughly you try to count the curve, red curve looking like that in this cluster variety, which are like one contact point with a boundary. And now there is a picture which is completely similar to the previous one. This moduli space has expected dimension d minus 2. And so if you fix a tropical type of dimension d minus 2, you should be able to count the corresponding zero-dimensional strata in the moduli space, and you will get a Gromov Witten count. So the difference with the toric situation is that here the moduli space might not be of the expected dimension. You really need some virtual technology. And the count which appear here is a count which has been first defined by Gross and Siebert in the context of mirror symmetry for log Calabi-Yau varieties. And so to partly answer Joel's question, so these numbers are the numbers which define the wall functions attached to the walls of the wall structure of the scattering diagram. So you can use them to determine the structure constant of the theta basis for cluster varieties, but they are not like equal to them. They are like, if you know them, you can reconstruct them by counting broken lines, the scattering diagram. You can recover the structure constant of the theta basis. So another theorem is that if your quiver with potential has trivial attractor DT invariance, then as long as gamma is not in the kernel of omega, then your rational DT invariant is simply equal to the sum, kind of sum of a tropical type, of these genus 0 log Gromov Witten invariants of this cluster variety. So, which means that under this condition of having trivial attractor DT invariants have a Gromov Witten meaning as counting curves in the cluster varieties determined by the quiver. So essentially, this theorem relates like two things you can do starting from a quiver. Starting from a quiver, you can look to quiver representations. Look at moduli spaces of quiver representation, you get these DT invariants. Or something else you can do starting from a quiver, you can cook up the cluster variety. And then if you want, you can count rational curves in this cluster variety. And the claim is that if you do these two different things, roughly you get the same answer. And the proof is kind of non-geometric. It uses the fact that essentially both sides are controlled by this kind of tree, attractor tree pictures I was describing before. And on the DT side, these trees can be organized into the so-called stability scattering diagram. Whereas on the Gromov Witten side, it's part of the general mirror symmetry story of Gross and Siebert that these numbers can be organized into a canonical scattering diagram. And what I can show, so it follows from the work of Udia with Mark Gross, that in the cluster, if you apply this general story to the case of cluster varieties, you recover the combinatorial cluster scattering diagram, which has been used by Gross-Akin Kilkon-Savage to construct this theta basis of cluster varieties. And then you can check that this combinatorial scattering diagram kind of matches this DT scattering diagram under this assumption of having trivial attractor DT invariance. Yes? You mean cis one?
That shows that the lowest order, scattering diagrams are how do you?
Yeah, that's so it's here that's the assumption that there's trivial attractor DT invariance is used here. It's kind of yeah, that's right. Actually, this in our definition of trivial, it's not only a vanishing, but also for the vertices you just get one. The DT.
What is it in terms of like sheet counting?
Okay, so here this story is about quiver with potentials. And yeah, so like if, for example, you assume like there is just for simplicity, let's assume there is no cycles or no loops. Then the statement is just that if you look at representation supporting a single vertex of dimension 1, there is a single such stable representation, just C at this vertex. And this thing will be the kind of the most obvious objects or quiver representations. And this one will kind of produce the initial walls you want. A vertex, exactly. That's right, exactly. Yes.
In the case in which QW is associated with some threefold, like in the case of the total space of the bundle of P2,
Yes.
if there is any relation between X sigma, X, and the threefold that you associate with the
So thank you for.
Let me answer the second question.
Yes.
Okay.
Yes.
So somehow what you're telling us
Yes.
is starting from a quiver,
Yes.
you can give a Gromov Witten interpretation of coefficient f,
Yes.
and also the wall omega by using some variety or some blow up of this.
Yeah, that's right.
But the cluster structure enters only in the proof somehow. Am I right?
And-
Now one could wonder if there is another equivalent proof of this theorem in which you don't use the cluster structure, or is the cluster structure on X relevant somehow in some other ways?
Yeah, that's how you might think.
You also think that these are key, it's only key to the proof.
Yeah, that's how, so you might think, which is actually what gross boundary Zibert did in dimension 2. You might think that this X story can be related to the toric story just by some degeneration argument. And maybe you might think that this formula is just a degeneration formula, and for that you do not need to see the cluster structure on X. And so it's not the way we prove it, but there should be a proof along these lines. It just, we did not wanted to think too much about this degeneration argument, but I'm sure it's possible. But in dimension 2, it is what gross boundary Zibert did. And it just for us, it was just easier to use this connection. In particular, we use this connection to say something else about mirror symmetry for cluster variety. So we had some other motivation to do that. Yes.
If W is equal to 0, everything is simplifies in a nice way? Or
So like if there is oriented cycles, having W equals 0 does not guarantee that there are trivial attractor DT invariants. And so, yeah. But yeah.
Can you say a little more about this tropical types? Like, so that's the T appearing that some of the tropical types? Is that right?
Yes.
I guess kind of didn't completely understand.
Yeah, so yeah, I mean, in principle, I mean, definitely, by itself, it's a combinatorial thing. And yeah, but the theorem says you need to sum over all of them, so somehow you need to find them somehow. But so for example, if you know the scattering diagram, it will tell you, I mean, if you go through, I mean, if you do this kind of tree, moving tree inside this picture, it will tell you what are the trees somehow. Yeah.
Sorry, so in the interpretation that this X is the Coulomb branch of what you do with Ethereum circle.
Mm-hmm.
And that your attractor points are like places where you have a particle that has zero mass.
Mm-hmm.
This assumption is basically saying that attractor points only correspond to vanishing hypermorphic BTS.
That's correct, yeah. Which is why it's something you might expect for like non-compact Calabi-Yau, but definitely not for compact Calabi-Yau, for which there will be interesting non-trivial attractor points. That's right. So it's one way to phrase part of the story in this physics language. And actually in the next lecture, I will describe a more speculative story, which is maybe more naturally phrased in this physics-like language. Okay, so in the last 5 minutes, let me answer Francesco's questions about if you look at a geometric situation like local P2, so it's a non-compact Calabi-Yau 3, and we discussed the fact that the derived category of sheaves on that as this description in terms of this quiver with potential. And so the first question you might ask is, can you, okay, so if you start from a geometric point of the story, as we mentioned maybe in the first 2 lectures, you expect that if you are like far enough in the space of Bridge-Jones stability conditions, your stability should reduce to this geometric notion of Giesecker stability, in which your objects are just like semi-stable current sheaves, not random complexes in the derived category, but just honest sheaves, which are semi-stable with respect to some ample line bundle. And if you look at these moduli spaces of semi-stable sheaves, you can get some geometric DT invariants as I need not by omega. And here I'm looking at sheaves which are like supported on P2. So they are like of rank 0 on the 3-4. They are 0 almost everywhere, but they're supported on P2. And on P2, they have some rank R, some degree D, and some other characteristic chi. And the first question you can ask is, do these numbers have a quiver meaning? Like as an example of the quiver DT invariance we have been talking until now, and in complete generality is not an obvious question because we focused on particular stability conditions for the quivers, these kind of king stability conditions, which are pretty different from the asymptotic Gieseker stability conditions.
Theta gives rise to polarization.
So here, because it's P2, there will be essentially one choice of polarization anyway, because it's pK rank 1. So in general, if you want to have a more general story, you will need to know how can you match the choice of polarization on the Gieseker side to theta, indeed. And maybe this question is not obvious in general. But here the claim. So in general, there are like different parts of the stability space. So if you go from one to the other, you might cross some walls, and so you might get different numbers. But it's a fact which actually in some language is already known since Drezé and Le Potier study of sheaves, moduli space of sheaves on P2, that if you have a numerical condition, if the slope d over r is between -1 and 0, then for every geometric data, you can find a correct dimension vector and a correct stability parameter theta on your quiver such that your geometric DT invariant is equal to your quiver DT invariant. You can go from geometric to quiver without crossing any wall if you have this condition on D and R. Yes?
If you have any toric threefold associated with the Q and W, do you have some way to prove a similar statement in which you intersect the standard art with the perverse art and see what are the semi-stable objects that are observed?
Yeah, so unfortunately, I don't know a general statement. It's a statement that people doing regional stability conditions should have answers, but I don't think they.
Yeah, because what you're intersecting the standard art with the perverse art.
Yeah, exactly.
You're looking at stable objects inside, and then you recognize that they are.
Yeah,
you're saying that in general.
Yeah, so yeah. Okay. Yeah, in general, I don't know. Because maybe in general, the global space of regional stability condition is not really understood. Like so. But this. Yeah, but the point is stability is like very far, whereas this quiver stability is like more in the interior, and you need somehow to find a way to go from one to the other. But yeah, but definitely there should be a similar. I definitely expect a similar statements for any like toric Calabi-Yau threefolds. Just I don't know. I think all the work necessary has not been done. And we also mentioned that for this quiver with potentials, this general conjecture that you should have trivial attractor DT invariance is known. So you can just combine what is on this slide with the previous main result to get a statement that says geometric DT invariance counting these semi-stable Gieseker sheaves on P2 have some interpretation of genus log Gromov Witten invariance of some geometry. And if you ask what is this geometry, so as we argue in compendiality, you should look at the X cluster variety of this quiver. So here this quiver has 3 vertices. So in general, you get some a dimension 3. So the cluster variety is 3-dimensional in this example. But this Poisson cluster variety has always some fibration into symplectic leaves. And here the symplectic leaves are 2-dimensional. And you can argue that all the curves you care about actually always live in these symplectic leaves. So you can reduce this 3-dimensional geometry to actually a 2-dimensional geometry that I have described here explicitly. I start with a toric surface whose fan has 3 rays, 1, 1, 1 minus 2, minus 2, 1. I get this toric variety, which has 3 toric divisors. And then I blow up a point in each of these toric divisors. This thing is like a log Calabi-Yau surface. And the interior of that is like a symplectic leaves of the cluster variety. And so the kind of concrete statement is that counting 0 log curves in this geometry, eating the boundary in a single point, is related to these geometric DT counts. So the last remark is that this kind of correspondence between DT on one side and curve on the other side is not an example of these DT/Gromov-Witten MNOP correspondence, because this thing happens when curve counting on the fixed threefold, where here on one side we have something related to local P2, and here we have something related to a different geometry. And in usual MNOP, you count ideal sheaf or curve. You do sheaf count, you do curve counting, where here you really consider like arbitrary DT invariants is omega RD count sheaves on P2 of rank R, and R can be anything you want. So it's about higher rank sheaves, but still it is related to counting curves somewhere, not in local P2, but it's kind of auxiliary geometry. And in this very particular example of local P2, there is some heuristic explanation for why it's the case, but this heuristic explanation will not work in general. In general, I will discuss some speculative story next time. In this very particular example, one way you can believe that your higher rank sheaves can turn into holomorphic curves is that if you believe in homological or mirror symmetry, your DT count of sheaves under mirror symmetry should turn into count of special Lagrangians and manifolds into the mirror of local P2. And so this mirror of local P2 is a three-dimensional non-compact Calabi-Yau. But somehow this three-dimensional geometry can be naturally reduced to a two-dimensional geometry, which is Calabi-Yau of dimension 2, so which is holomorphic symplectic or hyperkähler. And this three-dimensional spatial Lagrangian can be related to two-dimensional spatial Lagrangian in this hyperkähler geometry. And then if you have a two-dimensional hyperkähler geometry, you can do hyperkähler rotation to turn your spatial Lagrangian into holomorphic curves. And and if you identify the output of this hyperkähler rotation, the claim is that you arrive at this kind of correspondence, that you will get holomorphic curves somewhere, and the somewhere is a geometry I've described. So this thing only works in this situation. So here, in general, you count holomorphic curve in this cluster variety, which is a very high dimension. And here there is a coincidence that the geometry is two-dimensional, and so can be related to the original dimension 3 geometry. But it's a kind of coincidence. In general, it will not be as simple. And sorry for being a little over time, and I will stop there. Thank you. Mm-hmm. Yeah, so yeah, that's so. Okay, so here in this sequence, in this chain of correspondences, at some point there will be something very confusing happening. At some point, so okay, so in this mirror there is some SYZ fibration, but in this mirror there will also be this Landau-Ginzburg potential. And at some point in this story, the base of the SYZ fibration and the base of the Landau-Ginzburg potential, which in general are different things, in this story they will get interchanged. And so for example, the base of the Landau-Ginzburg model, it's an elliptic fibration with 3 singular fibers. But the base of the SYZ fibration is the base of a Lagrangian torus fibration with 3 singular fibers. And at some point when you do this hyperkähler rotation move, the SYZ fibration will turn into the Landau-Ginzburg fibration. Yeah, that's right. So this story, the Yu-Shen-Lins give a proof that part of this heuristic is correct, that at least at the geometric level, this hyperkähler rotation is doing what we want. So it's kind of compatible with that. So yes, so really the full picture that if you start from DT, you start with space of stability, and then under mirror space of stability is supposed to be space of complex structures. But if you move W, it's like the base of the Landau-Ginzburg fibration in this example. And then when you do hyperkähler rotation by Yu-Shen-Lin and all results, is base of the Landau-Ginzburg thing will become the base of the SYZ fibration. And along this flow, the kind of this DT, like scattering picture in the space of stability, at the end of the day, becomes a picture of the scattering diagram for tropical curve in the base of the SYZ fibration. So yeah, so definitely Yu-Shen-Lin and all story can kind of give the geometric, like part of the geometric story. So yeah, so it's not the way it appears through this two steps process. So Yes, this thing will be what we will see if you just do mirror symmetry and just run SYZ mirror symmetry. This is what should happen. But then we combine that with this hypercare rotation business, which kind of projects on the other side. And so at the end, which is why at the end of the day, you only see like usual tropical curve, but don't think like sections. So which is indeed a bit confusing. And it's really special to see like, if you think in terms of general toric geometry, toric polygons, it's really special to toric polygons having a single interior point. If you do this story for toric Calabi-Yau 3 with more interior points, this story will not work. This kind of coincidence that the two things are the same will not work. But still, the main result will hold. But we should find a different explanation for why it's true.
Any other question? Yes, please.
Can you maybe recall how this numerical condition of the slope comes in, and also in the result that you relate the deep invariance of this guy with that of the quiver with
Yeah, so this condition, yeah, just a condition which guarantees that there is no wall if you go from this Gieseker's shear stability to some stability which has a quiver description in terms of this particular quiver. So actually it's known that on P2, if you take any Gieseker moduli space, it's always like a quiver description, so you can always, without crossing any wall, you can always go to some quiver description, but maybe it's not this quiver, or maybe it is this quiver, but like with different, okay, maybe in convergentiality it's not this quiver. But if I want this particular quiver corresponding to a particular exceptional collection, if I want to arrive there without crossing any wall, I need some restriction on the degree rank of my sheaves. And it happens that this thing is a thing which works for this particular quiver. Yeah, so I think this trivial attractor DT property is kind of mutation invariant, so it should not matter. Yeah. Yeah.
Does this equality of geometric equivalent DT come from the equivalence of categories?
Yeah, so I mean, yeah, so in some sense, yeah, so the claim is that this kind of like derived category of current sheaves on this KP2, like maybe supported on P2, then this thing is really equivalent to this derived category of finite dimensional representation of this like Jacobi algebra of this quiver with potential. So there is such equivalence. And the claim is that yes, so there is like two moduli spaces which are the same, which induce the invariant. But the kind of reason why they're the same is that they are both counting stable objects in the same category, but a priori for different stability conditions. And so the claim is that under these numerical assumptions, these two stability conditions can be related without crossing any wall. So the moduli spaces are the same. So it's not a formal consequence of the fact that the two categories are the same. You need to deal with the fact that we look at stable objects. And so you need to match the stability points. Or argue you can go from one stability to the other without nothing changing your numbers. Yeah.
The BPS, the algebra, and so on.
Yeah.
Is there any relation between what you wrote at the level of numerative geometry and then this side of representation theory? Speculative somehow, I don't know. So is there any role, expected role?
So for example, so if you know that, you should say, oh, the left-hand side has this categorification. It comes from this BPS algebra. So you can ask, okay, what about the right-hand side? And this thing is something confusing because usually we don't think as Gromov Witten invariants as being something which should get categorified. But maybe there will be a partial answer to this question in the next lecture. So the claim will be that maybe you should expect Gromov Witten theory to be category 5 for things like holomorphic symplectic varieties or hyperkähler varieties. And then you might hope for some kind of upgraded version of this statement. But But yeah, it's like, it will be at a speculative level. Currently, there is no.
Okay,
No understanding.